Welcome to this explainer. Today, we're diving into the ultimate computer crash course. We're going to systematically unpack a foundational educational textbook that breaks down literally everything, from the absolute basics of hardware to the very first software programs you probably ever learned to use. I am super excited to guide you through this, so let's just jump right in.
Now, before we get into the nuts and bolts, the hardware and the software, let's ask a deceptively simple question. What actually is a computer, beyond that screen you're looking at right now? Because really grasping its core definition completely changes how you interact with it.
Here is our syllabus for today's masterclass. We've got the history of computing, types of computers, the anatomy, characteristics, and limitations, and finally, mastering MS Paint. Section 1. History of computing. Let's kick things off by looking at this massive historical timeline of devices.
It's pretty amazing to see how these calculating devices evolved across human history. We start 2,500 years ago with the abacus, that manual device developed by the Chinese. Fast forward to 1617, and English mathematician John Napier gives us Napier's bone for multiplication. Just a few decades later, in 1642, a 19-year-old Blaise Pascal develops the Pascaline for adding and subtracting. Then, jumping to 1823, Charles Babbage, who is often called the father of the computer, invents the mechanical analytical engine. This entire mechanical evolution laid the absolute groundwork for the modern electronic machines famously developed by companies like IBM in the 20th century.
Section 2. Types of computers. Now that we know where these remarkable machines came from, let's categorize them.
Okay, so let's dive into this comparison. We generally split computers into two camps based on their technology: analog or digital. Analog computers use continuous physical signals. Think of an old-school mechanical clock or a telephone billing machine. Digital computers, on the other hand, like your standard desktop or tablet, process logical operations using discrete digits. There are even hybrid computers that use both, but digital is definitely what dominates our daily lives today.
Moving on to Section 3, the anatomy. Next up, we need to dissect the digital computer system into its core parts to see what actually makes it tick.
So the crucial point here is this trinity. You've got your physical hardware, the parts you can literally touch and feel, like the CPU, monitor, and mouse. Then you have software, which the textbook beautifully describes as giving life to the computer system. These are your applications. But my absolute favorite column is the third one, the often overlooked humanware. That's the relationship between the computer and the user. That's right. Without you, the hardware and software just sit there. You are the critical third component.
And these three components build the core working principle of any computer. It's a precise three-step data cycle. Step 1 is input, receiving data. Step 2 is the processing unit, where those inputs are sent to the CPU to be crunched. Finally, step 3 is output, delivering that processed data as a desired result to your screen or a printer. Input, process, output. Super simple, but it is the literal foundation of all computing.
To actually feed that initial input, we rely on essential hardware tools. Take a look at the keyboard structure. You've got your alphabet keys, function keys up top, and modifier keys like Shift and Alt to change how other keys behave. And then there's the mouse. Our textbook points out the evolution from the classic, heavy rubber ball mouse, remember cleaning those, to the sleek optical wireless mice we use today.
Section 4. Characteristics and limitations. We know how they work, but what makes them so universally useful? And where do they actually fall short?
Well, computers possess some truly incredible characteristics. They operate at mind-blowing speeds, literally fractions of a second. They boast massive storage capacity, comfortably holding gigabytes of data. They offer extremely high accuracy. If your input is correct, your output is going to be flawlessly correct. But honestly, perhaps their best trait is diligence. Unlike us, a computer never gets tired or bored. It can perform the exact same repetitive task for hours on end with the exact same speed and precision.
But it's not all magic. What's really interesting here is the textbook's deadpan list of limitations. For all their power, computers have hard boundaries. Number 1, a computer cannot think, zero intuition. Number 2, it is entirely software dependent. But number 3 is notably and quite practically stated in our source text: a computer cannot be used on the dusty environment. It's such a great reminder that despite being digital powerhouses, these are physical machines vulnerable to something as simple as dust.
Section 5. Mastering MS Paint. For our final section today, we're going to ground all this theoretical knowledge into a highly nostalgic and fun practical application: making digital art.
Accessing a program like Microsoft Paint in a classic operating system like Windows 7 is a precise four-step navigational process. It perfectly demonstrates that input and software interaction we just talked about. You click the Start menu, choose All Programs, go to Accessories, and choose Paint. Boom! You're telling the CPU to pull that software from the hard disk and display it right on your monitor. Once you're inside, you have a wealth of tools at your disposal in the famous ribbon panel. You've got diverse brushstrokes, geometric shapes, a full color palette. And this is exactly where your HumanWare steps in. The software provides the digital canvas and tools, but it absolutely requires the human operator to input the creative direction, dragging the mouse to draw lines, and applying colors.
Finally, the critical last step. Once your digital masterpiece is complete, we have to complete the data lifecycle. By going to the File menu and hitting Save, you are instructing the CPU to take that visual data currently in temporary memory and commit it permanently to the hard disk's storage. You give it a file name, hit Save, and your work is preserved.
Which brings us to the end of our foundational journey. And it leaves us with a truly fascinating question. We've traced the lineage from the 2,500-year-old Abacus all the way to the digital processing of MS Paint. But as technology rapidly evolves, as we move past rubber ball mice, physical hard disks, and dusty environments into this crazy era of cloud computing and AI, what will the next generation's Computers 101 textbook even look like? How will HumanWare adapt next? Definitely something to think about the next time you sit down at your keyboard. Thanks for joining me for this explainer, and keep on learning.